Hi, my name is Meet and I will be talking about personalized compatibility metric learning. This is joint work with Anurag, Yenliang and Larry from Amazon. We will start by introducing Personal Shopper, which is a styling service by Prime Wardrobe. For customers who enroll in this service, their experience goes something like this. First, they create a profile by filling a survey which has questions about the customer's preferred styles, colors, fit, and so on. Some of these questions are displayed on this slide. Next step, our stylists, who are experts in fashion, pick pieces for the customer based on their survey responses and using help from an AI model. Customer can then preview their picks and choose up to 8 items to try at home for free. Once are delivered, they have 7 days to try them on. Once the 7-day try-on period ends, they are charged only for what they keep and the rest can be returned for free. Now, let's get to the problem we are specifically trying to solve. For Personal Shopper, we wanted to recommend sets of items which are compatible with each other in the sense that they go well with each other in an outfit. This notion of compatibility is subjective and each customer might have their own idea of compatibility. For example, in this figure, while both Alice and Becky may like wearing the pair of jeans at the center, Alice may prefer wearing flats with them, whereas Becky would want to wear them with heels. We propose a neural net architecture named PSNet to learn a compatibility metric which is personalized to each customer. PSNet is short for Personalized Subspace Attention Network. We will use this figure here to talk about and explain the details of our approach. It has many different moving pieces, so let's go through them one by one. Let's talk about the features. Our model takes in as input pairs of item images and customers' ratings on them. The images are first converted to vectors using convolutional neural network ResNet 18. Now, let's discuss the subspace attention network. Instead of learning a single notion of compatibility, we use style subspaces to capture multiple notions of compatibility. Subspace embeddings are calculated from the image feature vector by applying learnable masks via Hadamard multiplication. This equation on the right gives a mathematical description of the model. This entity within the parenthesis corresponds to subspace embeddings, and we can see that the final embedding is calculated by applying a weighted sum operation over them.
Now, let's discuss where these weights come from. For this, we first learn customer embeddings for each customer using their preferences on single items using a matrix factorization algorithm. Once we have these embeddings, the attention weights are made a learnable function of the customer embeddings.
We have the subspace embeddings and the attention weights. We get embeddings for each item which are personalized to the customer. We want this embedding space to reflect the compatibility notion of the customer, in the sense that items which are compatible with each other should have embeddings closer to each other, and vice versa. To achieve this, we use contrastive loss, which makes positive pairs converge towards each other and negative pairs diverge away. Now, let's talk about our training data. As shown in the screenshots, customers have the ability to provide us with their feedback on individual items as well as pairs of items. Their feedback is recorded as a binary yes or no signal. In addition, we also get compatibility feedback from our stylists in the form of labeled pairs of items. For PSNet, we only use the feedback from customers. To create our training dataset, we need to do some pre-processing on the images uploaded by the sellers. As seen in these examples, some of the images also have a model and other clothing items in them. We crop these images using a YOLO3 object detection model before adding them to our training dataset. Now, let's talk about the experiments we did. Since there wasn't any prior literature about personalized compatibility of pairs of items, we also created our own baselines to evaluate our model against. We created 3 different baselines. In the first 2 baselines, we removed the customer embedding input from PSNet and trained a non-personalized model. For the first baseline, we used ratings provided by our stylists to train the model. For second baseline, we used ratings provided by the customer. These baselines were used to gauge the improvement in offline performance from using a personalized model over a non-personalized model. In the third baseline, we removed the subspace attention mechanism and effectively used the only subspace embedding as our final embedding. This baseline allowed us to measure the impact of having multiple subspaces. To these baselines, we also had other choices when deciding our network architecture. For our loss function, we chose contrastive loss over triplet loss since it does not require sampling and therefore has less noise. We also tried different ways to get the subspace embedding from the image feature vector. Another important hyperparameter is the number of subspaces we use, as it captures the number of complementarity notions learned. We tried 2 different values of this hyperparameter and found that using 3 subspaces works the best. When we compile the metrics for all our baselines and our base model, the results look something like this. The metrics mentioned here are relative to our main model, PSNet. PSNet outperforms all the baselines we discussed in metrics like ROC, AUC, AUPRC, precision, and recall. Based on these findings, we realized a few key strengths of our approach. Making the attention weight a function of the customer embeddings improves performance. Also, ratings available from customers are more useful for learning their preferences compared to non-personalized ratings from stylists. This confirms the hypothesis that compatibility varies from person to person. Moreover, we also found that using multiple subspaces instead of just one also improves the offline performance. We hypothesized that each subspace is capturing different dimensions of compatibility such as color, fit, and style. However, a deeper analysis of the individual subspace embeddings is yet to be done. In addition to that, there are some other extensions to this work which we find promising. We can rethink how we are using the customer context in our model. For example, instead of using matrix factorization based on individual items, we can use matrix factorization on pairs of items. We also want to extend this model to include items from all categories and incorporate customer profile information. Thank you for listening.